All right, guys, so if we're recording, so let's get started again. We're going to continue. So we finished getting our data, creating a data loader, etc., with the iris data set. So the next step is to build the neural network architectures. So in this case, we're going to play with several architectures that you should be familiar with. I will be using um, the electronic whiteboard here for this part. All right, so let's get started. So if you notice, I'm going to grab, I have two examples. I have an MLP and I have a deep neural network, right? So we're going to play with these two architectures. I'll start with the MLP first. You can see that there. So I'm just going to bring it. So if you notice, the definition is exactly what we did with the GPT. I'm using object-oriented programming again. So this is the approach that we will use all semester. So I have a class. In this case, I'm going to call it MLP-net. I inherit the NN module, right? Then I have my two functions, which are init and also forward. Okay, so I have these two functions. You guys were familiar with this already. We have the super init for instantiating the inherited class. Notice here in init that this is the constructor and I'm providing in here x means and x deviations. So this is where that comes in. If you remember, we've calculated the means and the standard deviations, and now we're just essentially passing them to our class, and we're going to have them essentially as constants in there, right? So that way we can normalize and denormalize within the architecture itself. So notice x means and x deviations gets assigned to these internal variables of the class. Then after that, notice I'm going to use the famous NN linear, right? The building block of my neural nets to define my architecture. Notice that now I'm going to be adding activation functions such as sigmoid and softmax, which you already are familiar with, okay? So this is the softmax function. So I have this init class, and then I start to define the forward function, okay? So my forward function here is where I actually process the data, right? Now, if you remember, I've shown you guys that we have at least two approaches in PyTorch that we can use to define an architecture. It can be this approach where we, plug in X into linear, and then we have an output, and that becomes the input to the next step, right? Or we can use NN sequential, right, which is the other one. So NN sequential we'll use when it's a lot of code, like CNNs, like the GPT. That's where it makes sense to use it. Otherwise, I use it here, although that's preference. Very likely, you guys may have other preferences, and you're free to use things as you want. All right, so notice here then two things that you may have not seen before. When we initialize the class, we pass x means and x deviations. It's going to be like a constant that gets embedded in the network. And then the forward, we give it x. And here, we're going to need to standardize it. So this is the formula, x minus the means divided by the deviation. That's it. The data at this point is scaled. Do you guys understand? So that's our approach, okay? Any questions on that? That's the math of scaling. All right, great. So essentially then, what does this mean? The X, when it goes into training or it goes into inference, it's in the scale of the person that knows how to use it. So it's got, tons of coal, liters of natural gas, whatever it is, that it's going in the correct units, and it's going to get scaled here. Then X goes into the first linear layer, linear 1, which is defined up over here. Then the output is X, which goes into an activation. that goes out as X, and we continue doing that until the end, right? And until we get the prediction. So a good way of understanding this sometimes is to actually draw the graph. So that's what I'm going to do now. I'm going to draw the neural network, and I'm going to relate that neural network to this code here. All right. But hopefully this is something that in your minds is starting to become very clear. So this is Iris. It's 433. All right. So we're going to switch over to the whiteboard. Okay. Okay. So, right, Iris, I have 4. So this is the input. It's got 4 neurons. Then the next layer had 3. And then the final layer had 3 as well. So this is the neural network that you're creating. So remember, this one is fixed, right? Because it's the output. Why is it 3 neurons? Because we have 3 classes, 0, 1, and 2, Setosa, Virginica, and Versicolor, right? So you can't change this one. What about this one? Why is it 4? Because there's 4 features, right? And each, the vectors are 4. Petal length, petal width, sepal length, sepal. Got it? And then the middle one has 3, right? Why does it have 3? Because that's what I selected, right? That's my choice. You're the architect. So we can change this to be, I don't know, 15. Why not? Okay, so let's do that. I'm going to change it to be 15. And also, before I finish this, you guys should be experts in this now, right? You understand what's happening here. I have X times W0, the weight matrix, right? And that produces the next layer, which we can call hidden 1, right? We add a bias to it, and this vector is then run. The values in here are run through a function, which in this case is called sigmoid. The sigmoid function. Okay? Then what happens after that step? You have another weight matrix, W1. This vector times W1 gives you what? Output. You add the biases to it, and these values are run through another activation function. What was the name of this one in the code? Softmax. You should remember and know this because this is like the 3rd time we've encountered softmax, right? Softmax takes probability distribution that could be like 0.3, 0.5, 0.6, right? That does not add up to 1. In this case, this is 0.14 or 1.4, 1.4. Yeah. Yeah. That does not add up to 1, right? So if we run it through the softmax, this gets converted to probably 0.5, 0.4, 0.1. Now it adds up to 1. Do you see that? That's what that does. Questions? What's sigmoid? All right. So here in the softmax, we have no choice. We have to use softmax because this is for the classification step, right? So it's a classification distribution. But in between layers, we have alternatives like sigmoid, tan H, ReLU, GeLU, etc. We've already talked about ReLU. It is the hockey stick, right? And sigmoid has another shape. So we always plot these things as being like this. Our input values are these on the x-axis. Our output value from the function are going to be these vertical axes, okay? So for ReLU, change color, the hockey stick. What does that mean? If the value is negative, we make it 0. That's it. If the value in this vector here, if that value is negative, we make it 0. If it's positive, we just let it go out. That's the way it came in. We don't change it. So if it's positive, whatever it is, if it's positive, it stays like that. Got it? Sigmoid is this S shape. So sigmoid is like that, where this is a 1 and this is a 0. Do you see that? So this is still minus infinity plus infinity. You guys see that? So a number here, like minus 2000, is very close. It gets converted into very close to 0. A number over here, like plus 3000, it gets converted into a number very close to what? 1. Very good. And in between, there's going to be a point like at 0 where it's 0.5. I didn't do this perfect, but actually it's pretty close. It's like 0.5. Make sense? Tan H, same thing, but slides down. So tan H would be something like this, I believe. So the same function, but just slides further down, -1 to +1. Got it? Double check that one, but you play with them. So sigmoid is a very so initially when neural networks first started out, they had no activation. So okay, so this thing here, so we are at the stage where this is actually important. XW plus B is a linear transformation. This is what it's called, a linear transformation. So once you start adding these functions, sigmoid and softmax, you make them nonlinear. So they can actually, in a way of thinking about it is, when you have data, right? Linear just means that it's like that. And nonlinear means that you can build more curvy type shapes. It translates into that. So the thing that gives neural networks power is not just these linear transformations and everything, but it's the fact that you can also transform the data with these functions at these ideas of nonlinearity, right? That you can create other, because of how it transforms values into via ReLU or sigmoid or tanh, you just give it more capacity. Exactly. Trill is only a GPT trick. Exactly. So that's not related to this here. Yeah. Go ahead. What's the word activate? So activate, I think, is more like um, if these two values are present and they connect to this one, and this has a meaningful value here, that's what I would say is an activation. Not necessarily. It's just that this path, maybe this one over here connects to that, and these two activate like that to tell you that this is the predicted class. The active, yeah, I mean, the definition of it is like it's over a threshold, but that's not really, I would think how you should rep. It's too like trying to make it like the brain, and it's this is not the brain. So perceptron. So if you want to go back to the 1940s, people were thinking about brains, and they created this thing called a perceptron, and then they like explicitly said if it's above 0.5, this class. If it's less, this other class. But here I wouldn't think so much of activation, of activating things. They are called activation functions. But essentially what they do is this, that they take a value that goes in, and they, based on this shape, they produce an output. So they are transforming the data, if you will, but not through the linear process of multiplying times weights plus a bias. Do you see that? So it's like a second type of transformation. Yeah. Yeah, so we have the normal linear transformation, but then also that vector then goes through this thing and that transforms the data further. Okay. All right. So anyway, so we were defining actually the architecture, right? And we said that this value here is 15. Okay. So what I'm going to do is I'm going to go back to the code now. Go back to the code here. And so here, this is the architecture that I'm defining. So I said 4 to 3, 3 to 3, right? Yeah, sure. But that hidden layer, right? So this is the input layer 4 to 3. So this becomes the number of neurons in the hidden layer. And then from that hidden layer 3 to the output 3. So if I want to change that hidden layer to 15, what do I have to do here in the code? And then this one, right? Exactly. Got it? So this is the one thing that you want to master, right? And I'll do an example with deep learning also today, but that's the idea. All right, so notice here. So then we have x first of all gets scaled. Then x goes into linear 1, which is 4 to 15. That vector of 15 comes out here. Remember, it has already the bias added to it. Then it goes into activation 1. And activation 1 is this sigmoid, this value. Okay? And then that x goes into linear 2. Linear 2 is this one, which is from 15 to 3. So it's essentially multiplying, right, hidden 1 with the next set of weights, right, and adding the biases to produce the next one. And then that vector x goes into activation 2, which in this case is our softmax. The last step to make that vector add up to 1. That probability distribution. Any questions? All right, great. So I've defined this architecture. We will now move on to the next step. So I'm going to hit run here. Okay. And then we will come back to the deep learning one once we finish this run. So as you can see, we're pretty close now. We're almost there. This function, if you remember, even though the GPT architecture was really complex, if you remember, I said this function is actually almost exactly the same function that we will use even for very simple neural networks. So here is what I meant. I create a function, train loop. It's got n epochs, the model, the loss, fn, and opt. Some of these I still need to instantiate. Notice, as I said, this is the process of training the model. This is where we're updating the weights, okay? Notice here we have 2 for loops. Do you see that? Why do we have 2 for loops? Because the first for loop controls the number of epochs. So it's the number of times we're going to repeat this process, okay? The second for loop, it's where all that code that we did before pays off. Because all of that work was so that we just had to do this one line of code. And it makes our life so much easier. So now I'm able to just do for xb comma yb in train DL. That's all I have to do. And this gives me my xb batch. So 16 by 4 is xb. And yb is what? So remember, I'm grabbing batches from train DL, right? So xb is 16 comma 4 comma 1. Yes, very good. Got it? All right, great. Now notice that this is important. 16 comma 1, but the predictions are going to be 16 comma 3 because the last vector has size 3. Do you guys see that discrepancy? Now, in the past, many years ago, you had to do then YB had to be one hot encoded. You would have to convert it into 16 comma 3 so that they match. But PyTorch, the engineers at PyTorch decided that everyone was doing this step, which was kind of unnecessary. And what they wanted to do was this approach, 16 comma 1 to 16 comma 3. So the loss function, cross entropy, actually is designed to work that way. It expects 16 comma 3 from the neural network and 16 comma 1 from the labels. Do you get that? So this is just a workaround that was made. All right. But it's actually really handy. Okay, so we grab for x, and then here it should be pretty straightforward. We grab xb. What happens to xb? It goes into model, right? What does model produce? Y-pred. You see that? This is your 16 comma 3. And then what do? We give that 16 comma 3 and 16 comma 1 to loss fn. Loss fn in this case, because it's cross entropy, is going to compare the difference and minimize that error. All right, for now, we'll spend a whole lecture on cross entropy, so don't worry about that for now. But just remember, this is where we're comparing the predicted to the real, and we're trying to minimize, learn from that. Okay? Questions? All right. So this loss, we've already talked about this, right? It's computational graph and everything. This is the last week's discussion. So once we have this whole computational graph, and we are kind of anchored at loss, which connects everything, we can go ahead and do these 3 steps, which do all the heavy lifting as far as training. If you remember, I said to you guys, we will always have these 3 lines of code. Zero grad just zeroes out the accumulation of the values in the gradients. Then we have loss backwards. What was this part? This is the differentiation, right? So we take the derivatives. I'll explain this also with a simpler example later, but just keep in mind, this is where we decide for the update, are we going to be adding or subtracting to the weights themselves? Remember that? Plus or minus. And then the step actually does the update, right? Plus or minus the learning rate to the weights. Got it? Any questions there? All right. So this step then is the same cycle, right? This actually, you guys had more questions than the other class, but for me, when I was learning this stuff, these 2 for loops actually were like strange to me, especially the whole idea that I would give the data. So see, my initial view was I'm going to give the data to the model once, and that's it, and it'll learn from that. And then when I saw that you would actually do 6,000, let's say n epochs equals 6,000, I realized, no, actually, you're giving the whole data set to the model 6,000 times. For some reason, that actually felt like cheating or something. It just felt strange. But I couldn't wrap my brain around that idea, but that's how it works. So the analogy I always give here is, children, when they're learning how to do something, right, they don't need to trip on a wire 6,000 times to learn, right? You see that? But that's kind of what's happening here. It's like it needs to trip on that line 6,000 times in order to learn. So it might be that, humans, obviously, even a kid has context, right? So it knows other things. So that's why it can learn faster. But essentially, yeah, you take the whole data set, you do the shuffling, and you're going to give that to the model 6,000 times. Yeah. Yes, go ahead.
Yeah, we don't have different heads.
We don't have different what? Heads? Well, we don't have any attention. In what sense? Oh, Y16. So you're thinking like 512, there were 8 heads, so 64. So I had to make that calculation beforehand, right? So here you're thinking 16. Do I have to make calculations? Is that yeah, you don't. I mean, Y16, because if we just give it one sample at a time, it's too inefficient. It's too slow. The GPU, you're underutilizing your GPU. 32, you could choose 32. Now keep in mind, Iris is like a toy data set. But if we were using Sci-Far 10 images that are 32 by 32, and by the way, they're also RGB. So it's 32 by 32 by 3. And now you're giving it 32 images. And that's not even the problem. The problem is once that batch goes into the neural network and you have to do a whole bunch of computations, you might run out of memory. Especially if, let's say you gave it 1024, it'll break. You see, so that's where it becomes relevant. But when they built this whole machinery, they're not thinking of Iris. They're thinking of images that are 300 by 300. The memory, it's always the memory. It's always the problem. The GPU can process 3264 up to a certain point, and the limit is RAM. Exactly. Yeah. There's also some theory that, giving it 32 samples at once, it helps it to converge better. There's different stories also that you have to know about. But a lot of the time it's just experimental. Okay? But yeah, but you have to think of it as they're building it for big stuff, not for these little data sets. Although we still don't want to just give it one, we give it 16 or 32. All right, so guys, this is the same function that I used to train the GPT essentially, right? X goes into the model, gives me YPred. YPred is compared to YB. Take the difference, the loss, and then we do this part and update the weights. And we just keep doing this over and over and over until we exhaust the number of epochs that we have. Any questions about this part? All right, so it seems like we're good. So we ran that. Now we're very close to running this. The next step is essentially running it, as you can see. So I'm going to notice here, I take the model is going to be MLP.net. Notice I give it X means and X deviations, right? And then I create my object opt from torch optim. Remember, I can use stochastic gradient descent as SGD, or I can use atom. It's always kind of the same. In fact, there's only one approach to do this, right? And that's stochastic gradient descent. There's no third or fourth or second even. Atom is just a better implementation of stochastic gradient descent. Notice that we link the parameters of the model here by doing this, right? So we tell that this is what we want to update. Right now, this may not seem so important, but there are situations where you have two models, right? Two neural networks. So you have to tell the optimizer, well, I'm not optimizing the weights of this one. I want to optimize the weights of that one, right? So you can imagine how it could be model 1 and model 2, and here we specify which one. And then the learning rate is provided. Then notice the loss function is going to be cross entropy. As I said, we use MSE for regression, cross entropy for classification. If you notice, this is the exact same thing we used in the GPT. It's amazing, right? So ChatGPT works the same as Iris, right? So that's, should be pretty amazing. It was all architecture, if you think about it, right? It's all about that transformer architecture, but a lot of this is still the same. And here we are. I hit the run, and now the model is training. So we're training on 120 samples. There it goes. I'm not running GPU on this one because there's no need. Notice that the loss function, we want it to go down. So it goes from 112 to 6 to 56. And it kind of stays at 0.55. Every now and then you see 0.67 again. But yeah. So we're training. So right now, I'm running 6,000 iterations or so, or 4,000. And every iteration, I give it the whole data set for training. I just shuffle it a little, but yeah, that's it. All right. So I think at this point it finished. So it finished. And notice that the loss stays at 55. So definitely you want the loss to go down. Just because it became stable like this, it doesn't mean that it's bad somehow. We got to look at the results. So the next step should be for us to measure performance. And here I have this nice function for classification problems that I always like to use. Essentially, I'm using sklearn, but this prints all the metrics that I could possibly want for this. And so we'll see a lecture just on these later. So I'll use this function. So now to measure performance, I'm going to use this piece of code. So let's talk about it. First thing is, notice I have this with torch.nograd. What that means is that you want to make sure 100% that the weights of the model do not get updated here. Because remember, you're kind of cheating here, right? If you update the weights of the model. Why? Because you're not supposed to update the weights in relation to the test set. Okay, so we just add this. If you didn't add this, then the weights of the model could be updated, right? And so then now you're looking at the test set essentially. All right, so we torch no grad, so that ensures that the model's frozen, so no weight updates. And then we just do for X real, Y real, and test DL, right? And we grab the X inputs, we send those into the model here. We then have Y pred. This vector is a vector of 16 by 3, right? But our labels are going to be 16 by 1. And so we need to do something like this. We use torch max, which will essentially return the index, right, of the highest value. Do you see that? So if we have 0.2, 0.2, 0.6, 0.2, then it'll return 1, the index of the middle one. All right. And so now this indices is assigned to preds, and now we can send preds and Y real into my function print metrics so that I can compare. So here I'm not doing any like loss minimization. Instead, I'm just comparing the predicted values to the real values. And there you are. Any questions, guys? So here's one thing that I forgot to mention, and that's why I was thinking. So if you notice here, when I created train DL and test DL, there is a little bit of a difference. When I specified the batch size for train DL, I said batch size, which is 16. But notice that in test DL, I didn't say batch size. I said all test data. Do you guys see the difference? This is a common error, actually, that sometimes students make because it may be my fault that I didn't specify that. If you said here batch size, then it's just going to take 16, maybe the last 16, and run that through the class, through the evaluation. You would be able to spot that because when you look at the confusion matrix, it wouldn't add up to 30. It would probably add up to just 16. So you just got to be careful with that. So an easy solution to that is to just give it all the test data at once, and that's it. Do you guys understand? So just give the model all the data. So in this case here, I said batch size for the test set equal to all test data. What is all test data? Is the size of X test, which is 30. Yeah? Question? Yeah. Repeat everything? Okay. In numbers, when I create train DL, this is 16. When I create test DL, this is 30. In training, yeah, we do want to load the data in batches. because, you know, for a lot of reasons. It's you know, it's training, it's slower, you're doing a lot of repetitions, a lot of epochs, it's going to slow things down. But in the test set, we're only doing inference. No training is happening here. So either you still use batch size, but then you have to do this. Give 16 to the model, predict, compare, store that somewhere, give another 16, compare, store that somewhere. That's just more code that you have to write. Or a simpler solution is give it all the data at once. It's okay here because it's just inference. And that way you don't have to store anything. Even if this was 70,000, I think it can handle it just fine because it's not training, it's inference. So give it 70,000 all at once, and it gives you the result for all 70,000. Did I answer your question? Any other questions, guys? All right, so that's it. That's what I was thinking about this. So I am giving it all 30 all at once. And so that's what I do here. So notice here I do from test DL, I grab X real and Y real, but this is going to be 30, comma 4, and this is going to be 30, comma 1. And so I predict the values, compare, and here I have my result. So what do you think about these results? So here we have, and I have a set of lectures just for this, but the metrics that you use in classification are accuracy, precision, recall, F measure, and they're all based on something called a confusion matrix. So the confusion matrix shows you where you misclassify. So for instance, it says that out of 10 were out of 11 here, 10 were classified correctly and 1 was incorrectly classified. Do you guys see that? Then down here, it says that out of 10, 9 were correctly classified and 1 was incorrectly classified. And then up here, it says that out of 9, all 9 were correctly classified. So that's the confusion matrix. And from there, we calculate these other values, precision, recall. They have different meanings that we will discuss later. But usually, if you just want to look at one metric, you look at the F1. The F1 is what is called a harmonic mean of both the precision and the recall. So if you want to look at both with one, you look at F1. But here it's great because it does well across all the metrics. However, this doesn't always happen. Why did this happen? Because our data is balanced. That's what caused it. So when you see in the wine quality data set, when we do the same exercise and it's no longer balanced, then these values are not going to be the same. Precision is going to be something, recall will be another thing. Accuracy could be 99. And you're like, yes. And then you look at your precision, it's like 2. And your recall is like 20. And so you actually didn't do well. You might, and I have an example of this later. So accuracy is actually a terrible metric, especially with an imbalanced data set, is like dangerous. Like if you're not, you might go very excited and come out of that meeting like crying. So, all right. Does that make sense? So we'll talk about it, but yeah, the class imbalance would be reflected here. All right. So we did a full training, right, of classification. So now what do we do? Well, the next step is let's try another architecture, right? Let's try a very crazy architecture instead of the MLP. Yes. You got a precision of 1? You guys got precisions of 1? And just 1 for everything? And you're using my same architecture and everything? I always get 93 here. Because I got this, I think, with the other class. You guys are sure that you're... did you just... Because I changed my architecture. I changed my MLP to 15. Did you guys change it also to 15? You kept it at 3. You see that? See that? What I have there, I think, is like a more optimal one. I can run it again. No, it shouldn't take long. So you guys left this at 3? Oh, you changed it to. Okay, so who got a 1 across all metrics and left it at 3? Okay, so a couple of you left it at. Yeah, I changed it to 15 because I'm just playing with it. But if anything, this shows that if you, oh, not, architecture is important, right? There's no science to that. Just try it, experiment. All right, so I'm gonna now change it back to 0.3. Is your dropout, did you guys also remove this or left it? You removed. Okay, so you are normalizing, which is good. And you're not using dropout. So this is commented out. Okay, so let's try this one. It might do better. Okay. Let's give it a second. Yeah, this is the process. At this point, I can't really, it's up to you guys to play with this.
Even if we retrain the model with the same number, we can get different.
Yes. Yes, especially because I'm using that, remember that random seed. So actually that's intentional, right? Remember, I call that the poor person's tenfold cross validation. So what that means is it's a cheap, inexpensive implementation of that. Tenfold cross validation is an algorithm that essentially you run the model once, then another time, then you run it 10 times. And it's keeping track of things, and it's supposed to give you, out of 10 runs that are randomized, the average. But it's a lot of lines of code and a lot of complication. So what I've said instead is, well, just make that random seed, and that's, 1 line of code, and then just manually run it 10 times and keep track of it. And your code is much cleaner, much smoother, but you're still getting the same effect, just manually. All right, so yeah. So definitely to answer to your question, yes, it's going to be different because of randomization. All right, so I trained it again. I'm gonna try the function, and now the performance, yeah, mine went up a little to 97, 96, and so on. So it did go up. Yeah.
Even with the other model.
Oh, ones? Yeah, I don't know. I can't. When it comes to, it's it's like that whole question of how is ChatGPT thinking about something. I don't. It's that's the neural network, right? There may be some variable in here. It could sometimes have to do with the architecture also that you have in your computer. So lots of things. Anyway, we have some time left. So now let's try the other architect, and let's go like crazy with the neural network, right? So let's build a very complex one, maybe 4 layers, something like that, just so that we play with that concept. And I think we can wrap it up there. So I'm going to grab this one. This one I made so it's 2 hidden layers. I'm going to modify this one to be 4 hidden layers. Okay, so I'm going to put over here. So I'm going to call this one DLNet. It inherits the NN module just like before. It has the init class and the forward class. You guys see that? So it's the same thing. Remember, I've said this many times. A lot of this starts to get very repetitive, which is not a bad thing, right? So it's reinforcement by just doing things. Notice that we still initialize with X means and X deviations. We have the super init. So now we have to make some changes here because I want more layers, and here, correct? So these are the changes. So let's go back to the graph, kind of draw it out, and then we'll come back to the code. So I'm going to go to the whiteboard. Whiteboard. All right, and new line. Okay, so what do I want? I want its iris data set. So there's a few things that I cannot change, right? So the input is still what? How many neurons here in the input? 4. And in the output, how many? 3. But I want now 4 hidden layers. I'm going to do 20, 15, 10, 5. Why that? One recommendation I can say is like when you're dealing with images and it's a really large image, like 784 pixels, and then you have 10 classes over here, then you want to funnel it, right? So kind of what I did here, but obviously this starts at 4. So this is definitely a common practice. Here it's more open-ended, okay? All right, so this is what I want. So let's go now to the code and create this. All right, so we're back in our collab book. Notice that the way that I write these makes it easier to modify. You just separate by, because we're consistent, we can just separate them out like this. So I have linear 1, activation 1. That's the first one, right? From 4 to 20, right? And then I'm going to have the next one from 20 to 15. So each one of these is a hidden layer. Yeah. So I need 4 of these. So I need 2 more. I'm not going to modify this one because if you notice, this last one has the softmax. So that is essentially the last layer. It also ends in 3, right? So instead, I'm just going to add the layers here in between. But I just have to be careful with the numbers. So that's 1. So now, linear 1, 4 to 20, right? Activation 1, that's correct. I'm using ReLU here also, the hockey stick, instead of using sigmoid. You guys see that? Now, I'm not, just because this model is deeper does not mean that it's going to be better. Okay, in fact, some of you already have 1. So, but, this just shows that we can create more complex architectures. The next layer goes from what? What is this value here? 20, very good. And this one here, 15. 15. Okay? All right, here we have to change the name. So this is going to be linear 3. And this activation is 3. Okay? Oh, yeah, sorry, 3. All right, now, oh yeah. This is the DL net. So I grab this architecture here. This one, DLNet, the one that's below MLP. And I just decided to modify it. So that one, you can also run that one, but it's just 2 hidden layers. And so just as an exercise. All right, so linear 1, activation 1 goes from 4 to 20. Linear 2, activation 2 goes from 20 to 15. Linear 3, activation 3 goes from 15 to what? 10. And then we have a linear 4, activation 4. And what are the values here? 10 and 5. Okay. Now this one over here, this would be linear 5. And this is the output layer, right? It's got a softmax, which we don't modify because that's just the last. So we can get the probabilities that add up to 1. So what about these values here? 5, and this one, oh, sorry. 5, and this one stays at 3, right? Because 3 output neurons. Everyone with me? Yeah? All right, great. That's it. So we've defined our architecture. So now down here, obviously here we're just declaring them, right? So we have to make the modifications down here. So the same thing here, we standardize our data just like before. We always want to do that. Then I have, oh, and there's a dropout that's been added. I need to talk, I'll talk about dropouts another time, but just think of it as, a step in between for now. So, right, and now, and the last one here, this would be linear 5, activation 5. So this is the softmax part. So all I need to do here is add a few more layers for 3 and 4. So this is going to be 3, 3. And then this is 4. Make sense? Are there any questions? That's it. That's how you create these different neural networks. Yeah. So now we have DLNet. Okay, we have the definition of it. This is a very deep neural network. Not necessarily something that's going to do better, but certainly. Now, we just need to instantiate this new model and run it. So model now becomes DLNet. We give it X means and X deviations. The optimizer is Atom. We map or we tie the model parameters to this. Remember, the model parameters are the weights and the biases. The learning rate is 0.003. We use for our loss function cross entropy, and we invoke the training loop. Okay? All right, so I'm going to go ahead and run it. And there it goes. So it's training. But now it's training with a deep neural network. Whereas before, I was using what? A multi-layer perceptron. And the definition is really, they're all the same, but just has more layers. The MLP just had 1 layer, so it's not deep learning. This one has 4 layers. It is deep learning. Yeah. Yes, please. Huh?
Neural network is that better or is smaller?
Neural network is at least that X times W plus B and an activation function. That is a neural network already. That concept. Multi-layer perceptron is we have 1 hidden layer in between. 1 input, 1 hidden layer, 1 output. Deep learning is this one because it has more than 1 hidden layer. It's just deeper. So that's where the name comes in. Deeper just means more layers. Got it? But they're all neural networks. I mean, the strict definition is there should be at least 1 activation function. But the perceptron it was a neural network. I mean, the first neural network, and it had an activation, a step function it was called, but it wasn't quite what these are today. Did I answer your question? Yeah. Writing it down. Okay, great. Yeah. Yeah, deep learning was coined by, I think, Jeffrey Hinton. So he just said, let's call this deep learning. It was deeper, right? So you have to understand, like, the math for this existed for years. Stochastic gradient descent was invented in 84, and actually they almost solved it in the 40s. Like the calculus part was solved in the 40s. They just didn't have so the problem they had was that they only could do like from this layer to this layer. They only thought maybe that let's take the derivatives, but they only knew how to go from here to the next one. But obviously, you want to continue going back to previous layers. Do you see that? And back propagation, the actual name of Geoffrey Hinton's algorithm, solved that. That not the derivatives, that was solved already, which is you would think the important part, right? But they couldn't solve that other part until 84. But even though all this stuff existed in 84, it wasn't until why you couldn't make these things deep because you didn't have enough data, first of all, and enough power, computing power, right? So it wasn't until the internet that they had all that data, like Facebook and Google, and then the GPUs from NVIDIA after 2007. But anyway, so we're running the model. It's done, right? So the model finished training. So now we should be able to look at the performance. We just have to grab this code here. And 97. So is it better or is it the same? This one was 97, 96, 96, 96. Yeah, they're about the same. But they are different architectures for sure. Okay. Any questions, guys? So deeper doesn't necessarily mean that you're going to get a better model, because sometimes it might be overkill, right? The model doesn't need that much capacity. Hallucinations. Well, that's a term for GPTs. Yeah, like overthinking it. Maybe. I don't know. I mean, what you know the mechanics of how it works, right? But the model decides what it's doing with the training, right? So how it builds that network. So yeah, it might. I'm not sure. I'm not sure what it's doing. Here we go back to this idea of why people didn't like neural networks. So I'll tell you guys a funny story. When I was doing my PhD, I approached my advisor and I'm like, let's use neural networks. What do you think his answer was? No way. Think about this. I still use neural networks, but it wasn't the central point of my work. So neural networks have been actually like sometimes they haven't been the preferred method in the past. Let's just say that. Because one problem is mathematicians and people, scientists used to say that there's no understanding of how they work, right? So it's not clear how they did things. People wanted clear models. So for a long time, there was something called support vector machines, which is actually what I ended up using as the central thing in my studies. I spent 4 years or more trying to learn how it works, and I haven't used it since. But the thing about it was, it was you could explain things really well with it. You knew how things worked. And so everyone thought that was going to be the solution. And they treated neural networks as more of an empirical, computational black box approach that will never work anyway. And it turned out in 2012 that it did work. And now it really works. So yeah, you need to have a lot of resources, but it still works. I mean, it's still pretty amazing. So yeah, the problem with neural networks has been over time that people have considered that they weren't like mathematically beautiful. That's honestly like there's a lot of snobs in that world. And so it wasn't mathematically beautiful. Other things were mathematically beautiful. You know, support vector. So I'll give you this idea. Like, you know, I told you about these nonlinearities, right? So you have a data set. Let me actually move to the whiteboard here. So to give you an idea what I'm talking about. So I'm going to go to the whiteboard. So you have a data set. This is a very simplistic example. Okay, you have that, right? And obviously, this is the line. Obviously, right? That's the line. But a neural network could do that. Could, you know, if you just, you know, if you have this same thing and you just use like linear regression or something like that, you're going to have errors because it can only produce a line. Do you see that? So that's your y equal x, sorry, xw plus b. Okay. But if now you create equal y, that's a neural network where it's the same thing and the activation function. That sigmoid thingy. You see that? So this can create that curve. See that? So that's if you just use this approach, you can only create a line. Think of it that way, right? If you create the same mechanism, right? The same line, but it goes into an F, which is that ReLU or sigmoid or whatever, the Y that comes out of it now is not restricted to just this line. It can be this curve. So it's a better, you know, for separating the data here. Okay. But the people in this world didn't like this approach. They thought this was beautiful, explainable, mathematically beautiful. This was not. So instead, support vector machines was a very elegant trick. I will give you guys that. What you would do is you would take this in support vector machines through something called a kernel trick. And actually things that you understand now, like vector projections and all these transformations, matrix multiplications, and you would do a step where you would transform the data from this. Notice that here, right? There's no line that separates these, right? You admit that. So you would project this into a higher dimensional space. So I'm gonna just to symbolize higher dimensional, I'm gonna add a third dimension in there. Okay. Right? You guys with me? So I just, you know, symbolically, we went from Rn to Rm, where M could be much bigger. Yeah, we just projected it to a higher dimensional space. And this is support vector machines. But what happens now to the data is what's really important. Do you see that? You projected it to a space where now you can separate it by a line. It's linearly separable. So that was the whole battle that they had for years. Like the neural network people were relegated because there was this group of other academics who just didn't like neural networks because they, you know, they didn't want something like this that could create the curves. Instead, they wanted to solve everything with a line. And so the way to do it was somebody named Vapnik created this technique, the kernel trick. So they would map things into a higher dimensional space. A better way of thinking about, so that was mathematically beautiful, well-founded. There was so much mathematical theory about that. And neural networks didn't have that. A nice way of viewing this is like this. Actually, I should have done this one, but it escaped me. This is the classic example, actually, of this idea. Obviously, there's no line that separates these two samples, right? There's no line. The correct thing would be like a curve, which a neural network can create, but they don't like the theory of it. Support vector machines came in and solved the problem. How does it solve it? It takes the data, projects it to a higher dimensional space, and now imagine that the following can happen. All the zeros here, all these zeros move out. I'm going to use a different color to about, you see that, but you have to imagine that they're all coming from in there. So you see that? So it's like you had the data in one sheet, you added a dimension, and now you pull out the data. And in this space, obviously, yeah, you can have a whole plane that separates. So for the longest time, this was the approach. It was called support vector machines. It dominated machine learning like you have like cannot even imagine. Yeah, go ahead. The thing, yeah, right, but with very deep architectures. So you're getting into another point. To do that, you needed very deep neural networks. In 2005, that wasn't really possible because we didn't, the computing power wasn't there. So actually, you brought up a thing that's also important. I've said the mathematical beauty of it, but also the fact that the resource constraints, right? That was the other thing. So people said, well, we should solve it linearly, but then we just need some little trick to map it into a higher dimensional space. So they were not wrong about that. I mean, there's logic in doing that because of the limits in resources. Today, with GPUs, look at what the GPT does, right? So many projections and transformations. But yeah, so that was kind of the two reasons why neural networks were not that popular. Yeah. All right, good. So I think we're done for today. So we covered, I believe, I wanted to do this. We've covered tensor operations and advanced algorithm, right? Which was the GPT. I wanted to kind of step back to something very simple and make sure everyone gets it, right? So everyone's good. All right, we will do one more of these that's simple, which is going to be wine quality, and that's going to be regression and classification, and then we're going to get back into hitting harder targets as we move forward. Okay. All right, guys. So we're going to stop here for today.